I guess let's get started. So welcome everyone. So we are getting towards the tail end of the course, and the next few lectures will see some of the real compressors and real issues with compressors now that we feel well versed with the basics. Okay, so let's get started. Today's lecture is going to be on image compression, and the next two lectures are gonna build on the basic image compression stuff which we are gonna do today. So yeah. So let's get started with today's lecture. So first, a quick recap. So last time, the first thing we saw was like the transform coding. We like delved a little bit deeper into the idea of transform coding. We did the KLT example. And one of the main things I want you guys to remember is the two knobs which you had to play with in the transform coding. One was like, what's the block size? Oh, this color looks so bad. Okay. What's the block size for your transform? And the second was like, how much do you quantize each transform stream, right? And this is like, we saw that in the audio compressor also, where you could play with the frequency cutoff as well as the number of quantized levels. And that gives you like a variety of rate distortion points to kind of choose from. So these two are very basic knobs, will mostly be available to you in all practical compressors in some way. And so question one was based out of this. So which of the following cases do you expect vector quantization to improve the lossy compression performance? Like, in the case of IID data versus non-IID data. And if you recall, like vector quantization always improves performance. We saw that even in the KLT example. Like if you can do it, go ahead and do it. It's basically mainly because of complexity that you're not able to do it. So this is both. And then in which of the following cases do you expect transform coding to improve the lossy compression performance? And this again, we know that in the IID data, there isn't really any benefit to be drawn. Like you could have just done whatever you were doing. So it's basically in the non-IID or correlated data case. Okay. So after that, we looked into DCT. We saw that, our KLT example that, okay, it's actually a lot of work. It's not practical and efficient. And DCT was one of the practical lossy compressor. Yeah, and this is just like a reminder of what the DCT was doing. So you will have some signal, right? You can have DC. So the first one is threshold 0. So you don't even truncate. Oops, sorry. You don't even truncate your DCT. You just keep it as is. And then you can reconstruct your signal Y, right? But the way you would like to do this compression is throw away the low energy channels and components, right? And so if you have some threshold, you can zero out like all the higher frequency DCT. In that case, what you recover is this green signal instead of red signal. Something I wanted to highlight, I wasn't sure if this comment made through. Like if you look at the green signal compared to the red signal, you can see that the green signal is like a smoother version of the red one, right? So red is like a sharp triangular peak versus green is like a smoothened version. And that's expected because what you did was you basically removed all the high frequency components, correct? So this is like DCT. If you want to remember anything, it basically breaks down your input signal content into some frequency contents, and then you can throw away different frequency contents based on the statistics of the natural signal as well as what we care in terms of humans. And had a good question last class, which I think we didn't do good justice answering in class. So I have posted a much more detailed answer on it, which is like why DCT compared to DFT. The main idea is like, I'll just say like in DCT, you can show that you can get more sparse components compared to DFT. And the reason has to do with what we were saying in the class, like boundary conditions. If you want to look into the details, just look at that ED post. It's like, has much more detailed answer. Okay. And so the next two quiz questions were based out of this. So the first one was match the signals to their DCT. So you didn't have to do really anything. You had to see that like, okay, for different signals, we are just increasing the frequency. And so if you look at the DCT coefficient, your higher DCT coefficient will keep shifting towards right, because that's saying you have energy more and more in the higher frequency components, right? So here I've just arranged them in the sense of answers. You can match them on the grade scope. And then the second signal was like, okay, now we truncate the DCT for this particular red signal, where we remove the higher frequency components. And then what's the output DCT? Again, so what you would expect is that you're going to smoothen out the signal. You're removing the higher frequency. So it can't be the exact same signal. Can't be the exact same signal. It can't be this more high frequency signal, right? This is even more high frequency than the first one. Needs to be like some smoothened version of the other signal. Yeah. Any questions? Quite straightforward, just to get you guys comfortable with DCT. And then towards the end, we talked about this audio compressor where we showed this 2 different knobs which you can play with, like different frequency cutoffs, different number of quantization levels, and at different bit rate and different distortion. One knob might make better sense in terms of optimality. Like one knob might give you better distortion for a given rate, right? So for lower bit rate, you were changing color, so you were changing the frequency cutoffs. For higher bit rate, you were changing the symbol, so you were changing the number of quantization levels. Yeah. Okay, any questions until the last lecture part? Cool. So today we are going to learn about image compression. So exciting lecture. We're going to bring together everything which we have learned so far, from lossless to lossy. And in particular, we're going to learn about JPEG basics. I don't want to say we're going to learn everything about JPEG because it has like lots of small things, but we're going to at least, after this class, hopefully you guys will be able to talk about JPEG openly as like the basic components. Okay, and a lot of these slides are basically from these resources. So in particular, this YouTube video is amazing. I'd recommend you guys check it out. Very nice animations. Okay. So let's get started. So what is an image? So this is just an example of an image from Kodak dataset. So that's an open dataset. Okay, one way to think about image really is it's just an array of pixels, right? So you have some height times width times number of channels. So you have a 3-dimensional array where each pixel, you can think of it as being represented as 8 bits. Right, so if you have some image, you can think of it as R, G, and B colors, where each pixel need not be always 8 bits, but for today's class, let's assume 8 bits. It's just like something which is an 8-bit content. Okay, so you basically have 24 bits per pixel, or 3 bytes per pixel for different channels. For different heights and widths, right? So each pixel is roughly 24 bits, not roughly exactly. Okay. So this is just how you digitally represent image. This is just a digital image. And okay, so let's try to compress this image and see like why you would even want to compress this image. So for this particular image, this is a 764 times 512 dimension. So H is 764, width is 512, and then you have 3 channels, and each of them each pixel is represented by 1 byte. Okay, so the uncompressed size for this image is just, you'll multiply these things, right? These are the number of bytes you're storing in the image. And this turns out to be 1.1 megabyte, okay? Which is quite a lot for such a small image. Okay, so if you do JPEG compression on top of this thing, this image, like this is the reconstructed image which you get. But the size of this image is 27 kilobytes, which is, if you work out the maths, it's 40x compression. And I'm going to go back and forth between these two. Let's see. Do you guys see any difference? I went back and forth few times. So, okay, this is uncompressed, this is JPEG. I'm going to just keep going back and forth between the two images. Again, I'm just going back and forth. So basically you couldn't appreciate any difference in the final reconstructed signal, but you chose like you needed 40 times less bitrate for storing the same image. So okay, we are doing something good, like this compression is working, we could have saved 40x space. But you have done this class, so you know it's actually a rate distortion trade-off. Nobody is really stopping me to compress it even further. So okay, let me try to compress it even further. And so now I compress it to like by 80x. So now my file size is, instead of 28 kilobytes, it's just 14 kilobytes. Now if I go back and forth, so this is JPEG 40x, this is JPEG with 80x. Okay. Do you see something now? Right? So as you keep decreasing the rate, you start seeing a lot of these blocky artifacts. So as to say, you see here, like you can see maybe different contours. Here on the face, you can see like different pixel values. So this makes sense. So what it says is like JPEG, when compressed even further, now you start seeing distortions which might not be acceptable, right, to the end consumer. Let me compress even more. So this is what happens at like 137x. So now this image is probably pure garbage, like no application, no situation you would probably accept it, right? So clearly JPEG couldn't compress our initial 1.1 megabyte file to something like 8 kilobyte. At that point, it's clearly not doing very well. Yeah. But JPEG is really old, right? There has been a lot of work on image compression over the years. And this is what you see, like, if you compress it using one of the relatively more newer image compressor. So this is compressed using something called BPG. And again, my file size is 8 KB, so I'm working at the same 137x compression. But this is the image you guess. So again, so this was at 137x compression, same rate, the reconstructed image. And this is what BPG gives it. So I think for this one, I don't really have to go back and forth. It's quite obvious, right? So clearly, even though JPEG has stuck around for a really long time and you still have a lot of images encoded using JPEG, there is a lot of room to improve over JPEG. And we'll touch some very basic ways to improve. We'll talk about like basic BPG components also today. But then basically there are a lot of places to improve. It's like a rich field. You can improve compression. We don't really know if we have hit the optimality, so as to say, yet in terms of the design of the practical compressors. And in next lecture, actually, so BPG is still something which is in some sense traditional, where you have hand designed rules. In next lecture, we'll also learn about like ML based compressors. So if you know, like machine learning has taken the world by storm. Similarly, like you can apply machine learning to compression and get even better performances in terms of the rate distortion, really. And that will be next lecture. So wait till the next one, which will be after Thanksgiving. Okay, so this is what you get using an ML based image compressor. So again, let's go from the top. JPEG, 8 KB, BPG, a modern traditional compressor at 8 KB, ML based at 8 KB. So the differences, can you see? It's much, oh, sorry. This one jumps. Okay. I don't know if you were able to see, but the face is like much more smoother. Like we'll post these slides, go look at them. When doing image compression, it's always tricky because different displays can throw away. So it's always a good idea to look at the source material, just a general thing. Okay, so this ML-based compressor we'll learn about in next class, but the main idea is there's like a lot of room to improve your compressor, practical compressors. Right? So, first main point, like you can get incredible performance gains. Like you can get 40x to 137x gains without noticing any noticeable difference, right? That's huge. That's basically why people rarely actually store uncompressed images, right? So in fact, like if you have a camera, like something like, if you have a DSLR camera, it actually JPEG compresses your image by default, even if it's not storing it losslessly. If you would have heard of PNGs, PNG is a lossless image compression format, but again, like JPEG is much more ubiquitous, right? Like it's just present everywhere. And that's just because why do you want to pay almost 2 orders of magnitude extra space for something which is gonna look exactly the same? There are like bunch of different image compressors. There's something called JPEG 2000. There is something called BPG, which we're gonna talk about, but there is also AWIF. There is JPEG XL, which is actually one of the best traditional image compressors which are out there in terms of performance. And then there is ML based. But as you get better and better performance, obviously your complexity also increases. And depending on different situations, you might want to use the different compressor, right? Okay, everybody with me? Excited? Nice. And so this is a really old paper. Which introduced the JPEG compression standard. So this is from 1992. And what it says that, like, it's very interesting to look at this thing here historically. It says that majority of modern businesses and consumer usage of photographs and other types of images takes place through more traditional analog means. So in 92, you weren't really storing everything as a digital format. And the key obstacle for many applications is the vast amount of data required to represent a digital image, right? So like the uncompressed size was actually one of the main reasons people weren't even moving to digital storage of multimedia applications. And now if you look at it, you see like, okay, lot has changed. See again, like from the same paper, use of digital images often is not viable due to high storage or transmission costs, right? But we know a lot has changed since then, right? Okay. So lossy compression. Let's look at the problem definition of like what do we want to do in this particular case. So you start with some image, right? You encode, you get this JPEG file, you decode and you reconstruct something, right? So we have now looked at this rate distortion examples many times. And then your original image and reconstructed image are not exactly the same, right? And one of the important things is like how do you compare how good they are, and that was done using distortion metric. And so far we have been sticking so far a treatment of distortion has been around mean square error, right? So we developed theory around mean square error mostly. We looked at transform coding examples around mean square error. We looked at quantization, right? This is just what mean square error looks like. But let's do an exercise for images, okay? So, okay, here are 6 different images. So this A image is my source image, okay? So given the source image A, which of the following images would you prefer, like visually? So which one do you think is a better reconstruction of the image A among images B, C, D, E, and F? Again, not a trick question, just shout out. Okay, B. Does everyone agree? Or does someone feel there is some other image which is a better reconstruction of image A? Okay, B is correct, right? So it's clear, right? Like if I have to choose among B, C, D, E, F, I'll choose the compressor which gives me B, for example, at similar rate, right? Compared to C, D, E, F. Now let me ask a different question. So given this source image A, what do you think, like which of these images B, C, D, E, F would a compressor which is designed to optimize for mean square error distortion would prefer? Yes, shout it out. Okay, I see a few shrugs.
Maybe F.
Maybe F. Okay.
It looks like it's the same except a few
like salt and pepper noise kind of white and black pixels. Okay, somebody said F. Actually, this one was a trick question. All the images B, C, D, E, and F actually have the exact same mean square error as compared to the image A. So a compressor is agnostic to any of these images. Like if you are designing a compressor which optimizes for rate distortion, and as a distortion it only cares about mean square error, like all of these reconstructions are equal. But that is clearly wrong, right? Like you don't, I don't know, like B and E are clearly not, you wouldn't prefer those two reconstructions equally. They are like clearly very off. You would prefer B more. So what I want to highlight here is, even though we have been working with mean square error, that is not the right metric for a lot of multimedia compression, right? Because we as humans don't really care. We are not comparing mean square error between a reconstructed image and the original image. We have our own visual pathway which does like different things, and that's what we really care about, okay? And actually there is a lot of research which has gone into understanding human perceptual laws, like all the way from like neuroscience, psychophysics to like designing these compressors. And it's really integral, like in the sense, a lot of time, a lot of experiments, a lot of money has been spent into figuring out like, okay, how do I tune my parameters so that they are optimal for a human consumption point of view. Okay, and we'll learn more about it. So this is also another topic which is close to my heart. We'll learn more about it after the learned image compression lecture. So that will be a third follow-up lecture where we'll take a deep dive into, at least for the visual stuff, what humans care about. But for today's lecture and simplicity, let's just stick with the MSE for now, okay, which is mean square error. And what you will see is like that's what people did when they were initially designing JPEG. But then they inserted a lot of different heuristics at different places to account for that, okay, human vision acts in a certain way and MSE is flawed. So let me change some of the design parameters here and there. But that's really a rich area of field, and like you have lots of heuristics which are there. So sometimes it's very confusing if you would go look at the JPEG, certain design decisions, like why were they taken? Later on you realize, okay, there were some subjective experiments which were done to figure out those parameters to actually determine it. But again, like mostly it's MSE, which we are optimizing for now. Okay, so what are the problem caveats? And it's basically, so just certain things, because we have looked at various different settings. So the setting really is like typically we are compressing a single image and not really a group of images. If you are compressing a group of images, you can probably do something better than just compressing a single image alone. So since you are basically working with single image, non-asymptotic performance of a lot of these techniques is really important because you don't really have infinite data which you are working with. So you have finite data. All these artifacts do show up in compressors in different ways. And also data is most likely non-stationary, right? So it's not really, you're not gonna get IID pixel values really in the images, right? So transform, for example, is going to be a big help to decorrelate these pixel values. And actually we'll be using all the tools we know so far to build this compressor, right? So like on the lossy side, we know about scalar quantization, which is extremely fast, but not the best. We know about vector quantization, which is extremely good, but gets really slow as the number of dimension increases. We know about transform coding, where we decorrelate the data and then use the simpler scalar quantizer. And finally, we haven't really explicitly talked about predictive coding, but it's not that hard a concept to think about, right? Like, so when you are doing lossy compression, maybe you can predict the current symbol based on the past symbol, and just do the subtraction. And if you can do a really good job at predicting, you need to spend less bits to encode it. So this goes back to the context-based lecture, right? Like if you have a better probability model, you have a better compressor, like if you recall. And we'll have a quiz question in today, so you can just revise your predictive coding in terms of lossy compressor, but it's not really a fancy idea, right? You can use the past, it's like we have looked at it in homework 3, we have looked at it in lectures, you can use the past context so as to say to predict the next one, and that will improve the performance in terms of lossy compressor. And basically all of these tools are used for making your image compressor. Cool. So now that we have set up the problem, let's think about how we would compress this image. So your image, again, is just an array of pixels, height, width, some number of channels, for now RGB. Any thoughts? Like throughout the first obvious thought, like what can you do to compress this image? Let's not even worry about distortion for now. Let's just think about what can be decent ways to compress. Okay, one idea I got was large block of colors. Any others? We'll use that. Even more simpler, maybe. Or it's okay, just throw out ideas, we'll see them in next few slides, mostly, or during the next hour. Any other thoughts? Like, so all of you know a lot about compressors now, don't worry. You just got this HWC kind of data. Don't even think it's image data. You got this array. what can you do? No takers? Okay. Really the first obvious, simplest thing you can do is throw away half of the data in terms of height and width, right? You can just downsample the original image, which basically goes from making your image from HWC to maybe something like H by D, W by D, and C. Okay? So for example here, I just reduce this image in terms of height and width by half. And immediately I have got 4x compression, right? I have basically thrown away, like I have reduced the rectangular number of pixels by 1/4. So like this gives you 1/4 of the compression, 4x the compression. And then what do you do at the decoder? You need to do the inverse operation. So this is lossy compression, right? So we lost information when we did this downsampling. What you can do at the decoder is, like, if you know about upsampling techniques and signal processing, things like, I'm just gonna throw the terms, it's okay if you know, if you don't know, it's fine. You just think you can upsample. But you can do, like, I don't know, bicubic interpolation, Langchos interpolation, things like that, which is just filling out values between two particular discretized signals. You can do that at the decoder, and that will recover you something of the original size. And then you can compute the MSE between two, which will give you some distortion, right? And then you can obviously, like, play with the rate distortion by changing this factor D. So instead of 2, I could have done 3, 4, 8, 16. Nobody's really stopping me. And this sounds really stupid, right? Like, oh, I just reduced it by half or by 16. But actually this is one of, I would say, the primary ways in your rate distortion curves are even made in image compressors. So if you think about, like, images, what has really happened? Like, we used to talk about, let's take example of YouTube. We used to have 240p, 360p, 480p. Like, we used to have these terms. So these were basically referring to the height and width of your images or videos, right? And as you keep increasing the resolution, you have much higher quality videos and images, like 4K, for example. That's like amazingly detailed image, but then obviously you are paying the cost in terms of rate, right? And many times, maybe if you just have, I don't know, a very dull scene, you are not really watching, I don't know, your favorite action movie, it's probably okay to just watch it in 720p or 1080p if you're watching, I don't know, not a nature documentary, a boring documentary maybe, right? And so in practice, so we're not going to talk much about it, but in practice, again, this is one really common way in which people do multimedia compression. Like, you would downsample your 4K image to something like 720p, and then your TV on the other end, when it receives 720p, it upsamples it to something like 4K. And then obviously it's not the exact same thing which maybe the director wanted to show you, or the whatever, if you were clicking a photo, wanted to show you, but you use it all the time. So it's one extra knob which we didn't really talk about during transform coding, but you have this knob when you are building this rate distortion trade-off curves for any multimedia. Similarly, for audio, you could have, for example, change the sampling rate, things like that, right? So you always have that option. So something to keep in mind. Okay, so this idea was like, okay, we haven't really talked about it, but very basic and simple. But another simple idea is, like, you can just quantize, right? So let's just quantize the channels. Now we'll stick with approaches where you don't change the height and width. So you want to keep the height and width the same, but we want to do something about the channel dimension. So another simple idea is you quantize this 3-dimensional vector RGB, right? And this we have seen, and now it's just basically quantizing the color values, correct? And so, okay, so in this image, we had 3-dimensional, each of these were 8 bits, right? So RGB, each of this was 8-bit. But now I can just represent this image using only 256 colors. Okay, so earlier I had options of 2 raised to 8 times 2 raised to 8 times 2 raised to 8, because I can have 2 raised to 8 possible values of R, 2 raised to 8 possible values of G, 2 raised to 8 possible values of B, and each of them represents a different color. But instead of using these many colors, this is how this image looks like if you just represent it using 256 colors. Again, I like to do this because it clearly shows me if there is any change between two images. So again, I'm going back and forth between the original image and the quantized image. Personally, I don't see much difference. So again, just doing this basic quantization gave us around 3x compression. Okay? Without really bringing any distortion in terms of how the image looks like. And the main idea here is like, obviously we don't have like whatever this number turns out to be, 2 raised to 24. We don't really need these many colors to represent this image. There are like lots of colors which will just never happen. Like those are just not natural. So maybe we could have thrown away. We didn't really have to consider that bigger color palette to start with. So you can keep reducing it. So this is when you keep 256 number of colors. This is how the image looks like when you keep just 16 colors. So like 6x compression. At this point, you start seeing some artifacts, right? Like it's actually quite obvious. Because now you only have 16 colors, you can't really express that image as well. So again, examples of rate distortion, right? You can keep throwing away more data, you'll get lesser quality. Okay, so this is like one idea, and this is also called like, so we just did like vector quantization on the color channels. It's sometimes also called color quantization. It was like one of the first ideas which was explored in this field. Okay, but how can we improve? So what else can we do in this particular scenario? If this is the image you are trying to compress, so far we used that, okay, our images don't really have that many diverse colors. What else can you use if you were trying to compress this? Yeah, your face seems like you want to answer.
You don't have to store the same color many times.
Yeah.
Several pixels are of the same color, you store one and prefer having a pointer point to that color.
Yeah, so that's exactly what we did in quantization, right? So we made a codebook vector and we pointed back to one of the closest codebook vector for each pixel. But you are almost there. So what you said was like nearby pixels have the same color, right? But actually, okay, even if they don't have the same color, they are somewhat smooth, right? Like natural images, it's not going to happen that I'm gonna suddenly have those black and white noisy images which we have seen. Natural images are smooth, like all the colors, like the scene which we are seeing is smoothly changing, right? So the pixels nearby are actually highly correlated, right? And this is an example. So these are just zoomed out shots from the image. So this is like this spot, this is this spot, this is this spot. And you can clearly see that a lot of these pixels are like highly correlated. So if you basically stick to some local, you can exploit the fact that I probably need even fewer colors, or maybe get away with like representing all of them with a single color, so as to say. Right? So the idea is really like, let's try to exploit I don't know what happened. Let's try to exploit the correlation between neighboring pixels. So that's like the next obvious idea. And this is an example. So this is called color cell compression. It's a technique which, again, so all of these are like really old methods. This one is like 1984. Where what people did was like, they said, okay, we'll take a 4x4 block. Okay, so that means like this, where was that? Sorry. This thing is 4x4, let's say, instead of whatever it is. And we'll represent each of these 4x4 block by 2 colors. And on the left, you see the original image. And on the right, you see the reconstructed image using just 2 colors among 256 for each 4x4 block. And this exploits the fact that within my 4x4 block, my pixels are highly correlated. So maybe I can just get away with having 2 colors. I don't really have to represent it with having huge number of colors. And again, as you can see, like both these images, at least to me, if I'm seeing from far away, looks okay. right? If you are careful, you'll see some differences, but really it's mostly okay. And the idea really is like, basically it effectively gives you like 2 bits per pixel. And that's because, so for each 4x4 block, we first need to store the 2 colors, right, for that block. So you need 16 bits per block. But then we also need to decide, like mentioned that, oh, you need to have some pointer to tell you like, okay, which color does this pixel belong to, right? So you also need to store a bit per pixel to tell you, okay, my first pixel belongs to color 1, my second pixel belongs to color 2, so on and so forth. Okay, so you need 16 bits for storing that sort of pointer, 16 bits for storing the color. So at the end you need 32 bits for how many? 4x4 blocks. So, sorry, 32 bits for 4x4 block. So that's like 2 bit per pixel, right? So recall, we started from 2 raised to 24 bits per pixel, and now we have gotten down to something like just 2 bits per pixel. And for certain images, this compression, like as you can see for this particular example, it's really good. Again, very basic idea of quantization. Okay, everyone with me? Like, people understanding what's happening? Okay, good. But again, like if now I zoom in on this particular image, now you would see like certain artifacts. So for example, you can see this eye. So this is like the same 2 images just zoomed in, and you can now see that, oh, see like 2 things. First, my orange color became yellow, and then you see this red pixel aberrations. And that's basically happening because again, I'm just representing my each 16 block by 2 unique colors, right? So you will have some distortion, and again, depending on the specific image and setting you are working with, might be acceptable or might not be acceptable.